Hello, ladies and gentlemen, boys and girls. It's lovely to see you and welcome to the Hartford Astronomy Group. We've got a really good evening planned ahead for you. And the format, for those of you who may be new to us and to remind those of you who are familiar, is that after my short introduction, I'll then pass over to Martin Weston, who will give you a little bit of a tour of things for you to look out for in the next few weeks. Following that, I shall pass over to Jerry Stone, and he's going to introduce tonight's speaker. And we're going to go on a very long journey from here to the edge of the universe in a very short time. So make sure you've got your seatbelts on. We will have the main talk and you'll be able to ask questions, and we will ask for you to use the chat facility so that then Jerry will field the questions to you, to Robin at the end of his talk. Following that, I will just wind up the meeting and formally close it. But of course, those of you who want to stay on and have a chat afterwards, it would be lovely to have a little natter with you. A very special welcome to anybody who's new to us. We hope that you will enjoy tonight. Well, we're sure you're going to enjoy the meeting. And we hope that you'll stay on perhaps at the end of the meeting and say hello to us and tell us who you are and how you found us, and just have a little natter. So that's the introduction over. I'm now going to pass over to Martin, who's going to tell us about the forthcoming night sky. Over to you, Martin.
Thank you, Alan. So let's see if I can start with stellarium. Can you see that? Okay, so I'm assuming that you can.
Sorry, yes, we can see it, just to let you know.
Okay, so before I completely block everybody off. Okay. Yeah, all good, lovely. Thank you very much. Okay, so I'm going to start with stellarium. I don't normally do, but I just feel that there is some interesting things to be looking at this time of year when we do get a clear evening. It's this is really a spectacular part of the year for us, especially in the southeast and south, because we've got the Milky Way running down here, and most of the nebulas and main activity occurs in the Milky Way, because that's where most of the matter is. So you get this conglomeration of nebulae and stars and various other bits and pieces along that line. So you can just about see that hazy lump there, which is the Milky Way. So I want to talk a bit about stars tonight, if I can. Normally in the summer, I normally try and point out the stars that will be visible to most people. These are the bright stars that we use to help us navigate away around the night sky. So at the moment, this star up the top here, Capella, is almost directly overhead. It's quite bright, quite easy to spot. And if we come down directly heading southeast, we come down to Gemini here, and we have two stars here, Castor and Pollux. They're quite interesting pair of stars. I'll just click on there.
Can I interrupt you there, Martin?
Yeah, sure.
That's not showing Castor and Pollux on my screen where your mouse was going, so I'm not quite sure
what's happening there. So here we go. Well, let's try coming back and see what's happening. So
could you try going on full screen, perhaps? Ah, right.
Is that any better?
Well, it's full screen better. If you'd like to pop your pointer over.
Yeah, is that Castor? Yeah, okay. Well,
you're in the right place.
Yeah, because when I'm running on full screen, it's obviously not working properly. So we'll do it from this view. Still can see okay. So Castor and Pollux. So here's Castor, interesting star, because it's actually, if I zoom right in, a binary. Come in here, you can see it's sister star there. So that's one, you can actually see that with a pair of binoculars or a telescope. So that's one to look out for. And sister Pollux, they're quite easy to spot. The two stars, they stick out because they, you know, you won't be able to see all these other stars around it with the naked eye, not in this area anyway, but these two really are easy to spot and easy to find. So once you've found Gemini, if you follow the legs of Gemini down, eventually you'll come to Orion. Now this is a lot of activity in Orion. So the stars I want to point out in Orion are Betelgeuse here, Bellatrix, Rigel, and Safe, or Safe, I'm not sure how you pronounce that. But probably most importantly is Sirius. This is the only time of the year we can see Sirius, and it's the brightest star in the night sky. Obviously, and the reason for that is not so much how luminous it is, but just it's quite close to us, which is why it appears so bright. But all these stars, if you look at them, are all slightly different colours. Betelgeuse, as you can see, is an orangey sort of colour. Bellatrix is more bluey, and Rigel is a blue-white colour. And it's quite interesting to note that Rigel is it's a supergiant, blue supergiant, and it's absolutely massive and really, really luminous. But it's so far away, it doesn't appear that to us. It does appear to be a fairly bright star. But it's much further away than Betelgeuse and the other stars in that particular constellation. I'll move up a little bit from Orion Hunter, and we go to Aldebaran, which is in Hades star cluster. Again, that's a yellowy orange color. And if we move up to this, which everybody normally can find, they do appear quite small stars, but they're easy to spot because of the shape they're in. They're sometimes called the mini plough, but it's actually the Pleiades. And if anybody's got or seen the emblem on a Subaru car, that's the same emblem, the shape of these stars. So that's quite an interesting thing to look at through binoculars. You probably won't be able to see the nebulosity around them through binoculars because it's quite dull. Now, one other thing I might just point out while we're in this point here, if we come down from Aldebaran, come down the leg, this star, Tiangian, we've got M1, the Crab Nebula, which is one of my favourite spots. Now you can actually see this, it's the misty blob in the telescope. It's a supernova remnant, and it was believed to have exploded around the 10th century. Chinese astronomers noted it was a bright star even in the daytime for many months. So it just shows these records are worth keeping and give us something to look at. Anyway, so that I really want to just go back to the stars. The subject I was talking about, the stars and their brightness and the distance they are away from us. So I'm going to change that. I'm going to close that. Okay, I'm going to have to open the window again. So I want to concentrate on my presentation this time. So can everybody see that?
Yes, that's fine.
Okay, so this is the classification for stars. And I can't see the top bit because the bar's right across. So it's the Hertzsprung-Russell diagram, and it just shows you it creates a graph really to show you how the stars, what their temperatures are. So at the bottom line here, we've got the temperature of the star. And at the side here, we've got the luminosity of the star. So, and also we've added the colors in here to show what they're doing. So the stars I was pointing out to you on the diagram earlier on, you can actually see them in here. So here's our sun here. It's what we call a main sequence star. And showing you here a lifetime of 10 to the power 10 years. So that's about 8 to 10 billion years. So it's sort of halfway through its life at the moment. And all these stars in this sequence here are just burning hydrogen atoms at their cores to create helium atoms. So these are the main sequences. So if I just point some of the stars that we looked at earlier on, so we saw Cirrus, there it is there. So its luminosity 10 to the power 2, temperature about 10,000 Kelvin, surface temperature. And then I said about Rigel being a supergiant. Well, here is right. It's a blue supergiant. It's up here at 10 to the power 5 luminosity, surface temperature about 10,000 Kelvin. There's Deneb, which is actually on the other side of the sky. I didn't show that at the moment, which is in Cygnus S1. Betelgeuse, another supergiant here, which is quite an orangey red color. Antares was another one I pointed out. Interesting, Polaris, which doesn't appear very bright in the sky. The pole star is actually quite a large star. It's a supergiant, and it's quite bright, but it's quite a way away, which is why it doesn't appear that bright in our sky. Aldebaran, I pointed out earlier on, is a giant. I said Castor and Pollux. Well, there's Pollux there. There's Arcturus, which is on the other side of the sky at the moment. Procyon was another one I pointed out, and that is a binary star. It has a white dwarf. White dwarfs generally are stars that have ended their lives and they become super dense white stars. So I thought that was interesting for people to see how these stars are classified, and this also gives you a lifetime from the smaller the star, the longer the life generally. So these tend to have a much shorter life. Supergiants have a very short life, and they normally end up exploding and become supernovas, and then sometimes, if the mass is big enough, black holes. Moving on, another interesting little bit here. I got the news the other day about SpaceX losing 40 of its Starlink satellites. It certainly won't upset me, being an astrophotographer. The things are a nuisance, but it's a lot of money to waste. But apparently, we've had a geomagnetic storm recently. These were only just launched last month, beginning of the month actually. And what they'd all asked the satellites to be able to turn sideways onto the sun, so that the most of the high energy matter material coming off sun wouldn't affect them, but they didn't work for some reason, and it's fried most of them, so they're all going to end up burning up back in the atmosphere and coming back to Earth. This I found quite interesting. I've known for a while and heard people talk about the moon slowly moving away, the various reasons for it to move away. So this bit of information I thought was quite interesting. So that one of the Apollo missions, some technology was taken up so they could accurately measure the distance from the moon to the Earth. Obviously this varies because its orbit isn't symmetrical, but they work it out over a year. So it's drifting away at 1 to 2 centimeters a year, which is causing the Earth days to get longer by 1/500th of a second every century. So I don't think we're going to see a big change in our lifetimes, but it is interesting to note that they say the moon is slowly moving away. But interestingly, scientists now believe that the moon does this from time to time, as it's not strong enough to actually break away from Earth's gravity, but it does slowly drift away. But then the solar wind is actually pushing it back again. So it's believed that it might even be an oscillation between it moving out and then moving back in again. But I thought that was quite interesting. So we were talking about supermassive, we're talking about red giants and large stars becoming black holes. I come across this the other day. Quite difficult to understand what a black hole is, so I thought it would be worth just this rather basic description of a black hole. I found quite interesting. So it's saying that a supermassive black hole explained. A black hole is a region of space, which isn't really, but I put an explanation for that there. The force of gravity is so strong that nothing, not even light, can escape. But anything can be a black hole. So if you were to get a person and you compress them down to the size of a quark, which is one of the building blocks of an atom, then that would become a black hole. So if we look at our sun, for instance, if you could shrink the sun down so it was just 2 miles in diameter, it would become a black hole. So in there, I've just changed a little bit there, just added a bit there so that it was a bit more accurate about actually a black hole actually envelops a region of space. It's not a region of space. So that's your black holes. We've been talking about the James Webb Telescope quite a bit recently, especially as it was only launched at Christmas. So I found this also, which I thought was quite interesting to know exactly what it's going to do. So the resolving power of this telescope is so unbelievable that it's alleged that you could see the signature of a bumblebee at the distance of the moon, which is quite incredible. But although that's fascinating, we won't be looking at the moon through it. I don't think it's not what it was designed for. So I thought just try and bring to people's attention what it was actually designed for. So here we have our cone of the universe from the Big Bang to the microwave background, which we can see now, obviously, in the microwaves. Obviously, microwaves are moving a lot slower than the high energy particles, so that's why we can see that then. Then we've got the cosmic dark ages, then the era of reionization when stars are forming and galaxies, and then to the present where we are here. So if we look on this chart on the right here, well, we see Hubble here, how far it can actually look back, and we've seen some incredible pictures of Hubble, what pictures it's taken. And we can look back to approximately 500 million years after the Big Bang. So if we're coming back to the curve up to about here. But James Webb is going to be able to go right back to 50 million years after the Big Bang. So this area here, which is completely unexplored to us, we'll be observing. So expecting some fantastic information coming back from that. And just to give you an idea of what area of the spectrum we're looking at with this, I've got Hubble here, which is mainly in the visible light section of the spectrum, a little bit into the infrared. And then we had Spitzer, which was completely in the infrared, going almost into the microwave, about halfway into the infrared. So James Webb is going to be overlapping both of these telescopes, overlapping Hubble here in the visible light spectrum, and overlapping Spitzer here in the infrared. A bit strange, haven't seen it this way around, because normally in most graphs you see it going the other way, but we've got the longer wavelengths, radio, microwave, infrared, ultraviolet, and X-ray and gamma at this end. So talking about James Webb, where is it now? Okay, so launched obviously on Christmas Day. So at the moment, it's actually on Monday, it actually arrived where it was meant to be, reached it, so they put there, it's reached the perch from which you can spend as much as 20 times more time in surveillance of the Big Bang. So it's traveled 1 million country miles to be where it is at this point in time. So hold on to your hats and let's see what happens. So really that's mainly it on the talk. I just wanted to show a few images that some of our astrophotographers have taken, because I think we've not been blessed with clear skies, but Steve's taken this wonderful image here of Bode's galaxy here and the Cigar galaxy here, and really superb detail. These red hydrogen alpha areas you can see in here. Well done, Steve, that's superb. Kevin's taken this one of the Rosette Nebula, which is, I should have shown you on when we were on Stellarium earlier on, which actually is one of the nebula which is in not far from Orion. It's just actually in Gemini, just on the edge of Gemini and between Gemini and Orion. But that is a fantastic image. He's got the whole wide field there, which is really good, so you can see the whole nebula right its entirety. But wonderful detail. These areas here, dark areas, are clouds of hydrogen that's obscuring the light. This is where these stars are being formed from these dark clouds. Another one from Kevin's done. This is the Flaming Star Nebula here, and the Tadpole Nebula here. And again, nice wide field. we've got lots of nebulosity showing that these two nebulas are connected, even if by this material here. Well done, Kev. Lovely. One I've taken as a rosette, my telescope's f8.9, so it's doing just the core basically. I can't get the outside bit with this particular telescope, but you can see the dust clouds a bit more clearly. That's a bit more magnified here, and actually telling the stars are aligned now. And this one I did last week, which is supernova remnant, the Jellyfish Nebula. That is quite a dim object. I put a lot of imaging hours to get this detail out, so I'm quite pleased with that. And that concludes my talk. Thank you very much.
Much indeed. Absolutely marvelous stuff there. Those photographs are phenomenal, aren't they? Brilliant. Thanks ever so much indeed for getting them ready and sharing them, and thanks to the photographers for all that terrific work you have done there. While you were looking at Orion, it reminded me that Terry Creasy, who does our sort of things in the night sky to look for, he picked a target in between Gemini and Orion. He's chosen Monoceros, the unicorn. I think that's a challenge to find that one, certainly in the skies I've got around me here. But, you know, unless you get challenges, you've got to have something to go for, haven't you? So again, thank you, Martin, and thank you, Terry, for giving us something really hard to look for. I'm now going to pass you over to Jerry, who's going to introduce tonight's speaker. So over to you, Jerry.
Thank you very much, Alan. Before I do, I must just mention a couple of things about Martin's talk. Firstly, I mean, we always assume that names of things in the night sky are absolutely ancient. I mean, Aldebaran, Betelgeuse and so forth really are. But I'm sure some of you must have noticed something in the constellation of Monoceros, which must be a little more recent. Hagrid's Dragon Nebula. And the other thing was about the distance of the moon. So this came about as a result of the Apollo missions that left laser reflectors on the moon, and by firing a laser, and we know very, very precisely the speed of light, and by timing how long it takes for the light to reach the moon, bounce off the reflector and come back again, you can calculate the distance to the moon very accurately. And because we've been doing this for over 50 years, we know that the moon is slowly receding from the Earth. The actual distance, and I really love this, the distance that the moon is receding from the Earth is 3.8 centimeters per year, which happens to be the rate at which your fingernails grow. So there you go. That's your personal connection to the moon. So on to the main part of tonight's session, and our guest speaker, I'm very pleased to introduce Robin Catchpole, who's currently working at the Institute of Astronomy at Cambridge. He was a senior astronomer at the Royal Observatory at Greenwich up until, oh gosh, it's almost 10 years now that he's left them. But he joined Greenwich in 1962 and was posted actually to the Royal Observatory at the Cape of Good Hope, where you'll probably say, yes, they do have better skies than at Greenwich. But he's been very busy. He has authored and co-authored over 120 research papers and articles. And tonight he's going to take us to, well, from here to the edge of the observable universe. Now, I have just got one of my books down off the shelf, and this was actually printed in the year I was born, 1955. And it has very nice drawing. I mean, there are no photos in this book at all, but a nice drawing of the Palomar telescope, the 200-inch, which at that time had only been working for 5 years. And in its discussion of galaxies and so forth, it says a calculation showed that the Andromeda spiral is at least 750,000 light years away. Well, we now reckon it's over 2 million light years away. And other discussions about the size of the galaxy here have been completely put out by things that we've discovered in more recent years. So to take us through that and to give us what I'm sure is going to be a fascinating trip, over to you, Robin.
Thank you. And I'm just going to share my screen and select that and allow, let me go there and play slideshow. And hopefully things are, let me just get rid of that. Hopefully you can see my first slide, can you?
Yeah. Not yet.
Sorry, can you, what was that? Did somebody say not yet? No, hang on, just hang on. Let me just try that again. Share.
There we go.
Good.
Coming okay now. Yes.
Good. You can see. All right. So I'm up and away. Okay. Well, let me just start by thinking a moment about what we call the universe. And what we have to realize is that we are part of the universe. And what we do is try and understand the nature of the universe through the medium of light. Light is the messenger of the universe. And through the laws of physics, we try and interpret what that message is telling us. But I think there may be a fundamental limit to what we can know about the universe, very similar to Gödel's theory of the incompleteness of mathematics that says you can never completely understand something of which you are a part. Now, light is the messenger, and the message that it brings is its spectrum. And in this is something that if it had been a live talk, I would have demonstrated. A slit of light with a diffraction grating in front of it sorts light according to its wavelength. And we see within the structures here the message of that light, which in this case comes from the sun. Now, in this case, what I've done is take an image of some streetlights down on the right here, Mercury streetlights, and here is the spectrum. And this pattern of color is, in fact, a pattern of emission lines, is the unique spectrum of the element mercury. So with this simple device of a diffraction grating, I have this mysterious power of being able to tell you what the composition of these lights is. And if I was to compare the relative strengths of the emission lines here, I would be able to tell you what the temperature and the pressure was in those lights. Now, my diffraction grating maybe costs a couple of pounds. In order to explore the universe, we now have spectrographs of the order of tens of millions of pounds. And of course, we all know that the story of the development of astronomy has not only been one of improving the size of telescopes and their resolution, but of exploring the widest possible range of electromagnetic wavelengths. And in general, the longer the wavelength, the cooler the gas or the elements of the universe we explore, the shorter the wavelength, the hotter. And it comes as no surprise that the stars around us emit most of their light over what we call visible wavelengths, to which the human eye is sensitive. Now, the other thing is light travels at a finite speed, and this gives us a very handy unit of distance, the light year. And this is a fun little thing that, again, I would have demonstrated to you in reality if I'd been with you. If you, in 1 second, light travels 7.5 times around the Earth. So if you take the tennis ball to represent the Earth and wind a piece of string around it 7.5 times, then unwind it, you will see it's a very convenient experiment, because on the scale of the tennis ball representing the Earth, then the length of this string is about 1 light second. And you can see I can just comfortably hold it out. That is just short of the distance to the moon, about 1.2 light seconds. So that gives you the distance of a light second. And if you want to find out how long a piece of string you need to form a light year, well, you just have to do a little sum here to multiply the length by the number of seconds in a year. And the answer that you get is that you need a piece of string to go around the real world, the world we are living on, about 1.25 times, about 1.2 times. So that's a light year. Now, the finite speed of light enables us to look back in time as we look deep into space. And this is this huge and unique advantage that astronomers have over every other science, that we can go from the present here and we can look back in time to the origin, or close as we can, to the origin of our universe. And of course, because it's a time and, if you like, a space diagram, we can put other temporal events like the birth of the sun. And as we go through this talk, we will look at different aspects of this timeline. So we don't see the universe the way it is, except very close to home. We have this advantage that as we look deeper, we see the universe at different stages of its life. Now, I always like to sort of bring things back to a human reality. And if we want to put our modern humans on this diagram, we have to take the last 100 million years and expand it up here, then take the last 7 million years when we had a common ancestor with chimpanzees, our last common ancestor, and modern humans, that's us, emerged in about the last 300,000 years. So let's go back to our exploration of our universe and start with the first star, of course, our sun, and that is about nearly 500 light seconds away. That time it takes light to get to us. And this is rather a nice image. Then it shows a living organism, a bird, and a planet, the transit of Venus, back in 2004. So that's about 8.3 minutes away, the sun. And now we can use this portrait of our solar system taken way back in 1990 from Voyager 1. And we see from the sun here, we see the planets Saturn, Uranus, and Neptune. And Neptune is about 4 light hours from the sun. So we've gone from minutes to hours, but of course, for the next stage of our voyage of discovery, we have to go to the nearest star in the sky, which is about 4.4 light years away. And that, of course, is one of the pointers in the southern hemisphere. And you'll see its companion up here, the other, it's about 100 times further away than this star, but of similar difference, which means it is considerably brighter. So we're all used to the idea of stars being at different distances. And as we proceed further, we've gone from our 4 light years to the nearest star. We now look at a bit of the Milky Way visible in the southern hemisphere, and we're looking towards the galactic center down here, and we're looking at about 25,000 light years as we progress further outwards. And just to remind you that in the same way we can represent the entire sphere of the Earth on a geometric projection. This is an ITOF or equal area projection that distorts shape. So we can represent the entire night sky, because the night sky is just a sphere concentric with the sphere of the Earth, if you like. And we have this amazing image that I'm sure you've seen before. It's not an image. It's actually, if you like, a graphical plot, because it contains, in principle, the 1,000 million stars observed by the Gaia project, and the colors are the colors of the star, and the black regions of obscuration are really just the absence of stars in the Gaia catalog. And nevertheless, this is only about 1% of the stars in our galaxy. And if we now move to longer wavelengths, the infrared, we see through this foreground of dust and gas that was cutting in the previous diagram, cutting up the regions of sky here and obscuring a lot of the light towards the galactic center. Incidentally, those are the Magellanic Clouds down there. If we go to the infrared, then we begin to see the bulge of our own galaxy. And we see this perspective effect. This as we move towards the plane, we see this increasing density of stars, which is just a consequence of us living towards the edge of this concentrated disk of stars. And you can see a slight flaring outwards here, because this is the bit of the galaxy on both sides that is behind us when we look towards the galactic center. So it comes as no surprise to recognize that we live in a galaxy that, if we could get outside it, we would be somewhere out here looking those 25,000 light years towards the center. And we're looking at typically this collection of 100,000 million stars. And if we were to look on it face on, we would see a spiral galaxy, very much like this spiral galaxy, with us towards the outside here, these spiral arms, and we would be, as we are, rotating at about 220 kilometers a second. It still takes about 225 million years to go around once. And again, to give you that sense of perspective, we have been around the center of our galaxy about 20 times since the sun was born. Now, it's only the order of 100 years or so since, well, not less than 100 years still, but not much less than 100 years, only about 93 years since Hubble put together information that had been available about the speeds, the Doppler shift speeds of these fuzzy objects in the sky, that we not only recognized that galaxies were quite separate island universes, is something they were once called, collections of stars, and not just places where stars were being born, in other words, a protoplanetary system. And he was the first one to publish this law that showed there was a relationship between the velocity and the distance of an object that he based on variable stars, Cepheid variables that he was observing. And so it's only for about just less than 100 years that we've understood the concept of galaxies at all. Now, we've already mentioned the Andromeda Nebula, and here it is, very similar to our own galaxy. We argue about the relative masses at a distance of 2.2 million light years. And when I talk about these distances and these things, I like to imagine what astronomers might see if there are astronomers on the Andromeda Nebula, and they have very powerful telescopes, so they can look at us on Earth. And what will they see right now, whatever now means? Of course, they won't see us. They will see the Australopithecines, who lived about 2.2 million years ago, and for whom the accessory of choice was not the mobile phone, but the hand axe. And I always think it's quite interesting to ponder what the light that is currently leaving stars in this galaxy today will illuminate in 2.2 million years when it finally arrives at our Earth. But if we are to explore the universe, then of course we must start looking a lot further. And this is the Fornax cluster, or at least these blobs are here, seen through the foreground of stars within our own galaxy. We see these individual galaxies. And this is at about a distance of 60 million light years. And this is a very important distance, because from here to about 100 million light years or so, we can just resolve, if we go to a galaxy like this one, we can just resolve the brightest stars as individual stars, and with something like the Hubble Space Telescope. And so we can identify individual variable stars in the field here. And we can, from the brightness of the variable star, we can work out the distance in centimeters, if you like. And of course, we can measure the radial velocities, which are the order of 1,500 or so kilometers a second, which greatly exceeds the circular velocities, the velocities of couple of hundred kilometers a second here, and the velocity dispersions in the cluster. And just to maybe kind of put it in its simplest line, and I don't apologize for using such a childish diagram, but this just makes the point of the expanding universe. And so we have an observation here today, and we have these two little cars. One is at a distance of 10 kilometers and it's going at 30 kilometers an hour. The other is at a distance of 20 kilometers and it's going at 60 kilometers an hour. And this is what uniform expansion looks like. And we can use our very simple schoolboy arithmetic to work out when when these cars were at the starting line. And we can work out the rate of expansion, the rate of their departure from us. H0, that's the expansion rate, in appropriate units is 3 kilometers per hour per kilometer, the rate of expansion. And so if we take the reciprocal of the Hubble constant, we get the fact they started 20 minutes ago, which you can do from this sum anyway. Now, a lot of people, we're familiar with the fact that H0 is 71 kilometers, well, 71, 72, 73 kilometers per second per megaparsec, which is, of course, the one thing we were taught never to do at school, mix our units. And so people say, well, how can the reciprocal of the Hubble constant be the age of the universe? It just doesn't make sense. Well, the reason is that we've mixed the units. And if we express the Hubble constant in the appropriate units, kilometers per second per kilometer, then the rate of expansion is 2.3 times 10 to the minus 18 and kilometers per second per kilometer. And 1 over that gives you that age, quite simply. So it's don't mix your units is the answer if you want to understand the meaning of these things. Now, the extraordinary thing about this uniform expansion is that everybody seems to be at the center. And this was a lovely little demonstration one could do in the old days of overhead projectors, just a random bunch of dots on a piece of paper, and then you put the piece of paper through the photocopier and magnified it a couple of % or so, and then you could lay the thing on any galaxy here. There we are, and or over here, and you can see all the other objects seem to be pointing towards it. And this was, just a fun way of illustrating that. And of course, it makes the point when people say, well, are we at the center of the universe because everything's expanding away from us? Well, yes, we are, because everybody is at the center of the universe, because what is this uniform expansion? Every point moves away from every other point. So there was a moment when all those points were at the center of the universe. So that's one way of looking at that. So what have we done? Well, very simply, we have measured the rate of expansion today. And so we can say there must have been a time in the past when the size was 0, and we call that the Hubble time. That is the rate of expansion today, just extrapolated back to give us the Hubble time. So this is the past, this is the universe we can see, and this is the future. Now, we know that the fate of the universe depends on the density of matter. And so we have, because we know the universe is full of matter, and so the question is, what is the trajectory of the universe? This assumes the rate will be constant for all time. This implies that all have the same velocity here, but the universe has been slowing down and maybe will go on expanding till it comes to a halt at infinity. And if there's a lot of matter, the universe will recollapse. And the actual ages of the universe depend on, again, the mass and its past history, because this is the Hubble time. This is, on this exaggerated scale, is half the Hubble time. Now, Einstein, of course, is the person who gave us the proper theory, the theory of general relativity, which is the theory appropriate to space-time and the expansion of space-time in the presence of gravity. And what he did was, the story is exactly the same, but he related the density of the universe to the geometry. And so the geometry depends on the fate. A high density has a spherical geometry. A critical density, which means expanding to infinity, has a Euclidean geometry, and a low density, a hyperbolic geometry. Now, we will come back to this. We will just move on very slightly to see that we now have a law, the Hubble law, which enables us to look at all the many individual galaxies that we have, that we see on this deep exposure of the universe, and enables us to work out their distance, assuming that the universe is uniformly expanding. And this enabled us to make this plot, which was made about 20 years ago. It is the location of about 250,000 individual galaxies, and it is 2 strips of sky in opposite directions. And so we are here in the middle, and the velocity, if you like, the redshift of every galaxy that could be measured was plotted here, and we see this foam-like structure that we see, this familiar foam-like structure. You'll see the structure thins out here, and this is an observational selection effect, meaning we only see the brightest galaxies at the greatest distances. Now, we're going to come back to this, and we're going to now just look around at some of the nearby galaxies and see what we think we know about the evolution of galaxies. But just to set the scene, I want to show you our timeline here. Here we are today. So that diagram was made out to about this distance. If you think this is all the time in the universe, then our 2DF survey comes out to about here. But let us look around at the nearby galaxies. And in this image, we see 4 different galaxies, and it is an image, so it's not a sort of composite. And you will see the extraordinary diversity of forms. This cross peanut butter shaped bulge, peanut shaped bulge we have here, and the disk of gas here, a giant elliptical here, and a spiral with a small bulge here. And when we look around, we see evidence for what is apparently and clearly the interaction of galaxies. And what we have come to realize is that the collision of galaxies, the interaction of galaxies, is an extremely important part of their evolution. And here we see 2 disk galaxies that are colliding, and they are merging. And you will see during this interaction, you will see those streams of stars. You can see streams of stars there. You will see limbs of stars stretching out very much like we saw with the Antenna Nebula. Now, I should add that this is entirely Newtonian, and the red glow surrounding the galaxies is the dark matter that makes up the majority of the mass of the galaxies. And it is this dark matter that is very important in governing the nature of the collision. So we've just seen a structure like this, and we see here with the Hubble the details of the interaction here. We don't have to worry about galaxy collisions. Andromeda will collide with us in a while, but galaxies are very, very largely empty space. So individual stars move past each other with almost no collisions. But the black holes in the center here will dance around each other and then eventually merge. And during the collision, the dark material, the gas clouds, feel the gravitational tug of this collision, and this causes the gas clouds to collapse and form new generations of stars. And you see the very bright, young, short-lived luminous stars that are created during that interaction. Now, we have recently come to realize the importance of black holes. We first of all realized that all galaxies contain black holes at their centers, or at least all large ones do, and they are supermassive black holes. And we have known for some time the importance of black holes, that here is a galaxy in the middle, and we see the results of these 2 jets, which are something like 2 million light years in extent across them, emerging from the center. And we see these individual puffs of material coming from the black hole. Now, we've already heard about black holes. And what is a black hole? Well, we've already heard about what a black hole is. It's simply an object where the amount of mass within a given volume is so great that the resulting force of gravity at the surface means that light cannot escape. In other words, the escape velocity of that mass is equal to the speed of light. And to make the Earth a black hole, you would require to compress it into a volume about this size, about the size of one of those large marbles. Now, it's very difficult to imagine any physical process that can result in densities as large as that. But if we had 1,000 million solar mass black hole, and we have black holes of maybe 6,000 million solar masses, then you would create such a black hole if you took 1,000 million solar masses of air at the density of air on the surface of our Earth, then it would spontaneously form 1,000 million solar mass black hole. So the densities that you require then become quite tractable. So let's have a quick look at a black hole, and this is Centaurus A, about 12 million light years away. And this object underwent a merger about a couple of 100 million years ago. We've just zoomed in here towards the center, and you will see this haze of stars, the dust and gas here reddening the background stars, the newborn stars up here. And somewhere in the middle there, we find lurks the center of this galaxy and the presence of a black hole that makes itself, it becomes visible in this infrared image with the taken with the Hubble Space Telescope. And you may say, well, how can a black hole be luminous? Well, if we were magnify this about 1 million times or so, then we might see something like this. We would see material in orbit, an accretion disk material around this black hole, and some of this material is making its way to the surface of the black hole. So if we could now look inside this feature, then we might see something like this. There is the black hole, here is the accretion disk material. It's very difficult. You have to get rid of the angular momentum to get material to drop into the black hole. And above and below the black hole, we have these emerging jets. So what do we see here? We see a very hot spot at the bottom of the jet here at a temperature of about 1,000 million degrees or so. The accretion disk at temperatures about 10 million degrees as material heats up. What is the slowing heating process? It's magnetic fields that will couple across this, transfer angular momentum outwards, cause, if you like, inductive heating. Some of the magnetic field disappears into the event horizon, along with some of the material. The other bits of magnetic field, we suspect, get twisted up here and channel the electrons that spiral along the magnetic lines and give these two jets. How do we know this stuff? Well, X-ray telescopes can make observations, not resolving it, of course, but observing gas material at these different temperatures at these different points. So the event horizon is the point at which where light once passed through this event horizon can no longer escape. We have a region around it called the ergosphere, where material rotates at the same rotation rate as the black hole itself. Black holes can have angular momentum, and outside that we have the accretion disk and then the emerging jets. And of course, we speculate about the nature of the singularity in the inside. So what does Einstein and general relativity tell us about black holes? Well, we're used to the idea that solar mass black holes, I mean, a few, maybe 10, 20 solar masses, that if you approach the event horizon, you would be shredded, you would be spaghettified, was a phrase that was made some years ago, and the enormous temperatures associated with the accretion disks would destroy you. But if we could find 1,000 million solar mass black hole that was floating in space, and there are plenty of, well, most of them are at the centers of galaxies, some of them quiescent. Let's imagine it's in a quiet phase. Then as we approach the event horizon, the gravitational tidal effects across our spaceship would not spaghettify us. The event horizon is a theoretical concept. It's not a barrier. And so as she, in her spacecraft, is crossing this event horizon, she's very happy. Her wristwatch is keeping good time. Everything's working normally. But as she looks out, receives photons from the universe, she sees his clock running ever faster. In fact, she sees the future of the universe running before her, whereas he sees her photons are getting more and more redshifted, and her clock is running ever slower and slower. He never actually sees her across the event horizon. She just fades away at the surface of the event horizon. But in terms of general relativity, she passes through and we don't know what happens then. Maybe she free falls for a few hours until she meets the singularity. But Stephen Hawking realized that actually we can't just have general relativity. We have to have quantum physics as well. And once we talk about quantum physics at the finer scale, this singularity, this surface is not a pure surface. It must be racked by the presence of quantum fluctuations in space-time. And it is from those fluctuations that we have the idea of particles being emitted, apparently being emitted by the black hole. So we don't know what the actual physics is that occurs at the black hole surface. There may even be some kind of firewall at this surface. So we still don't know about the details and much about the physics of black holes, let alone the physics of the singularity. Now, this is what I said we would see, but of course, this isn't what we would see. This, if you like, is the reality in some sense. It's an accretion disk around a black hole, singularity with a jet. But of course, we see things by virtue of the photons arriving from different parts of the jet, and they are subject to the gravitational field of the black hole. So we're over here, and photons coming from this part of the disk their trajectory is bent by the gravity of the black hole. We see the foreground disk here. So in fact, what we see is a distorted, the back of the disk lifted up, the front of the disk here, and the bottom of the disk here. So we see a very distorted image of that particular object. And as I'm sure many of you will know, we recently had this observation by the Event Horizon Telescope, which spans the whole world. And essentially, it works at millimeter wavelengths. Here's a typical millimeter telescope. And by simultaneously observing, in this case, M87, the South Pole Telescope couldn't take part in that because M87 is below their horizon. By simultaneously observing, it could act as one telescope with this aperture. But in order to do that, it wasn't possible to simultaneously combine all the fluxes. So what they had to do was run a clock and tape record the clock signal and the data signal, bring all the tapes together and run them through a correlator and obtain this particular image, which is 42 microarc seconds across, and is an image of that disk arrangement that we saw. So it's the shadow, if you like, of a black hole, because the black hole is causing this blank bit in the middle, but the black hole at its event horizon is considerably smaller. To give you some idea, it would be about 250 astronomical units in diameter, which is about, I think, about 4 times the diameter of Neptune's orbit around the sun. And just to give you another idea of just how impressive this observation is, I want you just for a moment to think, imagine this, this is a globe, a representation of the night sky, and we're used to the idea that its surface is divided up in 90 degrees from equator to pole. So now we imagine that we don't just have a globe, we use the whole Earth as our globe. And so, 1 degree is 60 nautical miles on the surface of the Earth. So on the scale of the Earth, here is the picture, 42 microarc seconds across, and on that same scale, using our Earth as a globe, this is the sort of size. You can see, in other words, it's only slightly bigger than a pinhead, and it's about 2 or 3 millimeters. And just to remind yourself that the actual observations were made at a wavelength of 1.3 millimeters. And in order to do this satisfactorily, we have to know the instantaneous location, allowing for the effects of continental drift of all the telescopes making the observation. It's just another way of saying this is one of these types of observation that is pretty absolutely amazing. But of course, we're still quite a long way from being able to observe the actual event horizon itself, but even so. Now, the other, one of the most important observations that comes out of our observation of black holes, of supermassive black holes as they are. This is the mass of the black hole in terms of solar masses, 10 to the 7, 10 million, 100 million, 1,000 million solar masses, black holes. There is a clear relationship between the mass of the black hole and this is a velocity here, but it is the velocity dispersion, if you like, of the bulge of the galaxy, which is an indication of the mass of the bulge of the galaxy in which the black hole lurks. So even though the black hole is only about 1% of the mass of the bulge, there is still this very clear relationship. And what this is suggesting is that the black hole is somehow involved in the evolution of galaxies. And I want to say something very briefly about, while we're talking about this, about how we see the evolution of galaxies. So we have the Big Bang, the cold dark matter clumps, under its own gravity, drawing the normal, the baryonic matter, which collapses to form the first stars in disks, and they form out of this collapsing halo of gas. And the halos of the hot gas cool, forming more disks of stars around these centrally collapsed central clusters of stars. So the disks and halos emerge with other disks and halos and form initially after a merger, as we saw in that simulation. We had 2 edge-on disks. They merged and they formed a spherical, or elliptical, halo-like elliptical galaxy. And then they sit quiescently, accreting more gas from the intergalactic medium that collapses, gives up its angular momentum, gives up its momentum as it collapses, maintains its angular momentum to form new spiral arms. And then we have more collisions, and we go around this circulation of forming spiral arms, colliding, merging, and so on and so forth. Now, it's very clear from, as we've seen from looking at galaxies that have black holes at their centers and jets, that there is a lot of activity that's going on. And in this case, we believe that this is M82 that we saw a picture of from one of your observers. This is M82. A lot of this gas is actually coming from grand starbursts and supernova explosions that is blowing material out of the galaxy. But the bit that we now have to look at more carefully is this bit where infalling gas creates new spiral disks around elliptical galaxies, followed by mergers. And here we see an example of the gas being blown out from the center of Sen A here. And what we now realize happens is that gas that's infalling, it triggers bursts of star formation, maybe in the new spiral arms around the galaxy. And a few tens of millions of years after it infalls and triggers this burst of star formation, the infalling gas feeds the central black hole. So the central black hole becomes active again. Jets then form, which blast material, clear gas from the galaxy, and thereby quench the star formation that's going on in the galaxy. And so that this star formation that was taking place is not allowed to see itself through to completion before some of the gas is driven away. Further away from the galaxy, it may actually compress gas and trigger more star formation. So what we see is this business that star formation is intimately related to the role of the black hole that not only grows as a result of star formation, but when it becomes active and creates these jets, and we see an active galaxy, it inhibits star formation and blasts material from it. And so that galaxies go through different stages of their lives when they're active and when they're inactive. And certainly our sun, our galaxy, has shown evidence for activity in the past. It is currently in a quiescent phase. So that's just something about the state of knowledge of galaxy evolution as we see it today, as we take our trip through the universe. Now, we've had a look at local galaxies and what goes on. I want to get back to this particular diagram, map of the local universe. And we assumed that the Hubble law would give us a scale that would enable us to look at the structures of the galaxy, of the galaxies around us. Now, the problem is that we only calibrated our expansion for galaxies within this sort of distance. This is as far as the Hubble can resolve individual variable stars, if you like. And we've used extrapolation, a very dangerous thing to do when exploring, deciding on the properties of galaxies over here. So what we needed was another form of distance indicator, and this turned out to be the type 1a supernova. And this type 1a supernovae are another story, but the bottom line is that when they explode, they can outshine in the 100,000 million stars of that entire galaxy. So very good potential distance indicators. And here we, back about 20 years ago, we started these surveys looking for distant galaxies in distant spirals where there might be a supernova. And here we see one at a distance of about 8,000 million light years. And what looks like a hot pixel turns out to be a supernova. And when we compared the distance of this object deduced from its redshift with the distance that was indicated by its light, this appeared too faint. It implied that the distance was greater than that implied by measuring the redshift. And just again, to put ourselves on the map, that was our 2D survey limit. You remember that we went out to? Well, this particular supernova is at a distance of about 8,000 million light years. So this is the distance we're looking at. So we're looking at discrepancies that are starting to arise around here. And this led to a survey that incorporated now many hundreds or even thousands of galaxies. And what this is up here is, if you like, distance from light measured against distance from redshift. And this looks like a pretty straight line. Well, it isn't. If you compare it with a straight line, you will see that, and when velocities are averaged, there is a discrepancy. And what this is saying is that in the past, the universe was decelerating as it expanded, and that is followed by acceleration today. And this is just a way, this is just exactly the same thing, another way of looking at the same lot of data, although this came from a much earlier result. And this is yet again, this is probably the most accurate redshift supernova distance for galaxies data that's been obtained. I don't have, oh yes, I do, 2019, this particular thing. And here we can start to actually decide on the models that best fit this data. But this acceleration seems to be well established. And so what we are seeing is that this observational work was done at this kind of distance, and this is the point at which we believe, somewhere around about here, that the universe starts to accelerate. So the extraordinary situation was that we didn't find the universe was performing either a very high density and collapsing, or expanding to infinity, or expanding forever and ever, but it decelerated in the past and now is starting to accelerate. And this, of course, was the evidence for this dark or vacuum energy that is driving the expansion of the universe. So that is, so the other bit of the puzzle is, of course, evidence for dark matter. And in order to get to the end within a reasonable time, I'm going to just speed up some of this, because I think you probably, many of you will know this already, that there are really 4 pieces of evidence for dark matter. Galaxy rotation curves, which is just saying that the speed of rotation, we saw the Earth going 200 kilometers a second or so, depends on the amount of matter that exists within the orbit about which the star is rotating within the galaxy. And when we add up the number of stars, we find that we don't have enough mass. And in fact, we find that when we measure stars out here, the mass is still increasing, where you feel all the mass should have been enclosed. And this suggests that there is a halo of dark matter. X-ray emitting gas in clusters of galaxies. When we look at a cluster of galaxies, we see that cluster. This is exactly the same sized image. There are those 2 galaxies with active galaxies emitting X radiation at the active black holes, X radiation at their cores. But we see this giant halo of gas, that the mass here far exceeds the mass of the stars here. But we can add up all the mass, and we simply don't find, unless we invoke the presence of dark matter, we don't find there's enough mass to contain this gas at temperatures of the order of 50 million degrees or so. We need the gravitational field to hold that sphere of very hot gas together. So that's one of the observations. And I said the mass of the X-ray gas far exceeds, I forget, maybe it's 5 or it might even be 10 times the mass of the stars. Velocity dispersions from galaxies was really the first bit of evidence to appear. And it was a point made by this fellow, Zwicky, back in 1933. Now, Zwicky was quite a character in astronomy. Sadly, I never met him, but I had friends who did. And the problem with Zwicky was he was extremely controversial. What he did actually was to look at the Coma cluster and measure the velocity dispersion, the speed with which individual galaxies are moving in this cluster. And that velocity dispersion is exactly related, just like the speed of a planet around a star depends on the mass of the star at the center. This velocity dispersion depends on the masses here. And he said there was just not enough mass to give those kind of speeds, but he wasn't taken seriously. And I just have to quote this bit here. It does show that if you want to be taken seriously, you do have to be quite nice to your friends and colleagues. As Zwicky described his colleagues, scatterbrains, sycophants, and plain thieves who have no love for any of the lone wolves who are not fawners and apple polishers, who doctor their observational data to hide their shortcomings and to make the majority of astronomers accept and believe in some of their most prejudicial and erroneous presentations and interpretations of facts, and who therefore publish useless trash in the bulging astronomical journals. Now, I don't know when he said that, but back in the 60s or maybe earlier. So there he was. So poor old Zwicky doesn't really get the credit. Well, he does now, but maybe if he'd been a little bit more friendly, we might have got to this dark matter a lot earlier. Now, gravitational lensing is perhaps one of the most beautiful and exciting, and I couldn't help taking this example of a friend of mine's water jug on this tablecloth, and we see the pattern of leaves here, but through the concentration of water, refraction here, we see the images of the tablecloth pattern totally distorted. And that's what we see when we see these gravitationally lensed images of a galaxy about maybe twice as far away as the lensing galaxy. The mass here is deflecting the light. So this is how it works. Here's our distant galaxy. Here's our foreground cluster. Light rays going off in all directions here. And a light ray that was going in this direction is deflected, and to our eye, when it enters our eye, it seems to be coming from that direction. So we don't see anything coming to us directly. We see an image over here because the rays have been deflected. And here are some, and this wonderful example that I saw where we have 1, 2, 3, 4 images of the same distant galaxy. And the great advantage is that the distant galaxy is about 11 billion light years away, and the foreground one is maybe, yeah, I haven't got the distance, it's much closer, but it not only magnifies the size, it magnifies the intensity, so we can look at star-forming regions in this distant galaxy in the way that we wouldn't otherwise be able to do so. Now, I think I am getting close to overrunning my time here, but I will just, oh, now I've got a few more minutes. I just want to make this point. This is an argument that dark matter is a real substance and not just perhaps a defect in observation, or maybe even a modification of Newton's laws, although this is something that is still being considered. But so let me just explain this picture first. Here we have 2 clusters of galaxies in this image here that have collided with each other and passed through each other. And what we have in the middle is the X-ray gas that is emitting X-rays, and we believe was associated with these 2 clusters. And during the collision, the gas atoms collided and the gas was essentially stalled here and is left behind. Now, the blue haze here is a measure of the presence of dark matter as deduced from the distortion of background galaxies behind the 2 clusters of galaxies. So what we think this is telling us is that we had 2 clusters of galaxies. The blue is the dark matter, the red is X-ray. So here we had them, they approached each other, they collided, the X-ray gas stalled in the middle, and then the 2 left. Now, what we would expect is that, say, broadly speaking, we might expect that if dark matter didn't exist, then we would, after the collision, we would have had 2 units of X-ray mass here and 1 unit of star mass here and here. So we would expect the maximum lensing to be taking place in this region, but the maximum lensing, indicating that this dark matter is there, takes place still around these 2 objects. And we would expect that dark matter, because it's dark, it doesn't interact with itself, that the dark matter would pass through and would remain with the cluster of galaxies. So that is an argument that dark matter is something real. Now, so what we have, we come back to the basic idea. Einstein says that density is related to geometry, and therefore geometry is related. Geometry can tell us something about the current density of the universe today. So how can we deduce what the geometry of the universe is? Which of these geometries apply? Well, here, and this is really the simplest interpretation, we can go back to the microwave background, and we know this is the state that the universe was when it was about 370,000 years old. And so we know at this stage, light and matter were coupled together, and we knew how density over densities were collapsing, and there was a certain size that had just managed to collapse once or expand once. In that time, a certain size, small things would have expanded, would have collapsed and expanded and collapsed and expanded. Larger structures would have never managed to collapse in the first 370,000 years. And you could say that the scale of the things that did manage to collapse, because the speed of sound, because it was light and matter, so the speed of sound was equivalent to the speed of light, correspond to the major structures within this thing here, this the structures within the microwave background that we will see, if we have a moment, have a scale of about 1 degree or so. So we can measure that scale length, and it's the order of 1 degree for the dominant structure here. And we can work out, we know what that size is in kilometers, because it's essentially the distance light traveled in 370,000 years. And we can measure the angular size, and from that we can deduce the geometry. And it turns out that the geometry is the simplest geometry of the angular size we measure. It corresponds to the Euclidean, the flat universe. And then we can say the geometry gives us the total density of matter and energy, which is the thing that rules its fate. Various observations fix the ratio of dark matter to normal matter, because we can work out how much total matter we need to make these lenses and compare it with the amount of matter in stars and so on. And the expansion rate fixes the ratio of matter to energy and predicts the actual fate of the universe. And that leads to this thing, which I'm sure you've seen before, this idea that we can work out what are the proportions of the various components of the universe today. And it's 73% the vacuum energy that's driving the expansion. And the total matter is the 4% of the baryonic stuff of ourselves, stars and planets and so on. And the mysterious dark matter makes up the 23%. We can look briefly at that 4%, and this is 4%. Most of that 4% is hydrogen and helium left over from the Big Bang. This amount is in stars. We're not too sure, but this amount is in neutrinos, elements beyond helium in the periodic table, and radiation, even though there are 1,000 million photons for every proton or neutron, radiation still makes up a very small amount of the mass energy. Now, I want to I'm going rather rapidly over a few topics here that I want to just make a point. People sometimes get a bit confused about the influences of dark matter and vacuum energy. Now, dark matter pervades the entire, the entire galaxy or a cluster of galaxies. Vacuum energy pervades the entire universe. But within our solar system, the density of the solar system is about on a unit of, are my units here? They are solar masses per cubic parsec, which just happens to be a fairly reasonable. So solar masses per cubic parsec, that's still a pretty low density. But within our solar system, if you draw a sphere around Neptune or Pluto, then the average density is 3 × 10⁻⁻⁻. Now, just to look on the other thing, the average density of the universe on this scale of units is 1.5 × 10⁻⁻17. So there's a contrast of 10⁻⁷ between the densities of within our solar system and within the average of the universe. So our solar system is totally matter dominated. It's only when you get out, you go out to the Oort cloud, then the densities drop to a mere 2 if you average over that sphere. Local stars 0.15, within a galaxy 10⁻². So you can see dark matter becomes important when you're at the average density of a galaxy, and certainly with clusters of galaxies, and vacuum energy only becomes important, even though it pervades everywhere, when you get out to the very lowest density regions. Now, to complete our tour, we must now, quickly go to the Hubble Deep Field, which of course was only about 1% of the area of the full moon, and there we have it, and there we have the history of galaxy evolution. And I just want to go, very quickly over a few last topics here. So we have observed out to the Hubble Ultra Deep Field optically, and as we heard that JWST is going to push us in a bit closer, not close to the microwave background, but certainly to a very exciting bit of the early history of the universe. And just to summarize some of the milestones we've had, the calibration of H0 by looking at Cepheid variables in nearby galaxies is out here somewhere. We then had the 2DF field here, gravitational lensing we see here, the supernova survey here, Hubble Ultra Deep Field here, the expansion of the universe starting roundabout here. And the lovely thing I like to say about the observable universe is that I always like, when I talk to the public, to bring human beings back onto the scale. And my favorite number is 100,000 million. There are about 100,000 million stars in a galaxy, about 100,000 million galaxies in the observable universe, and the order of 100,000 million stars. Cells, I think 86,000 million to be precise, in the human brain. And of course, with the interconnectivity of the human brain, that is much greater. Now, I just want to say maybe a last thing. And one of the triumphs of modern astronomy has been to use this distribution of matter, fluctuations of 1 part in 100,000 or so, and from that deduce the clustering we see today through what is called the lambda CDM, the lambda cold dark matter model. And the great challenge, and I'm just going to say this by way of ending, the great challenge today, and this was just to show that when we simulate the galaxy evolution, we are looking at a cube of about that projection, and there is that cube in these surveys that we're so used to. But one of the great projects of today is to ask ourselves, how did the universe actually evolve from here to here? This is what our theory tells us. What do observations tell us? And the only way we're going to do that is by seeing how the actual geometry evolves, by looking at the universe here we are, 2,000 million galaxies, looking at the way the clustering evolved to see if it'll give us some clues about the nature of what it is that is driving the vacuum energy. And I will just stop talking here with this final slide that makes the point that in linear time, we might think we know almost everything about the galaxy, and with the about the universe with the JWST, we might hope to see the first stars born. But if we look in logarithmic time, well, all the exciting stuff had happened far long before the universe was a second old, and that the fluctuations in space-time imprinted on the universe at the order of the Planck time are the basis for the structures we see in the universe when it was 300,000 years old or so, and those evolved through to the clustering of galaxies today. So I think since I've run out of time, I'd better stop at that point. And thank you very much. And I think I should stop sharing. Okay.
Wow, thank you very much, Robin. Well, as I predicted, a fascinating tour through our universe. And I still think it's incredible that our knowledge has been so amazing of what went on right at the very beginning, that we've been able to learn so much of that. And yet we still look forward to learning more. And we really hope that the James Webb Space Telescope will be able to help us in this. Well, now, looking down in the chat, there are no questions in there at the moment, which I only assume is because everybody is absolutely stunned.
Or they knew it all before. Yes.
No, I know this group.
So it's a really interesting, yeah, it's really interesting. Yeah.
I'm sure somebody's got a question or two.
Well, the biggest question you won't be able to answer, which is why does the quantum background energy be 120 orders of magnitude larger than what we actually get from the, it's just.
Well, yes, this is the, you can make an estimate of the what's called the dark energy or vacuum energy from considering quantum theory, and you can, as you have seen, we've made an estimate of it, and you're right, there is this discrepancy, this huge discrepancy. And of course this is I mean, the question is it the astronomers who are going to solve this, or is it people working on the Large Hadron Collider? And a few years ago, a friend of mine who is a string theorist said, well, he felt the Large Hadron Collider, it had found the Higgs boson, but it wasn't going to go any further. But there are now observations that look as though they're strengthening up from the Large Hadron Collider that may tell us that our basic theory of particles is going to break down, is that there may be some flaws in it. I mean, up to now, it has proved incredibly robust, but maybe this is not completely going to be the case, and maybe the Large Hadron Collider is giving us some clues. But the whole reason for doing this, trying to work out the equation of state, if you like, of this vacuum energy term, is the fact that we hope it may shed some understanding on what's going on in the physics of the very early universe. So who's going to be giving us this insight, and who's going to give us insight into the physics inside a black hole, this bringing gravity and quantum theory together? This is the big challenge.
It's a stunning thing. I mean, my personal view is some. I mean, when people always talk about general relativity, the classic is space-time curve and all of this sort of thing, and the general media doesn't really give enough quote to gravitate, because quantum requires a particle force field type explanation. So everyone tends to talk about curved space-time in that, but people like Lee Smoley and I can't even pronounce his word, says that has to sort of totally change, and there could be something,
Yeah, well, it's only when you get to the early universe that you get energy densities sufficiently high that the force of gravity is very important on the same scale of the quantum forces. In the universe we live in, as you know, the force of gravity is incredibly weak. So it really doesn't, when we're looking at electronic transitions in atoms, gravity isn't playing a role, not a measurable role anyway. So so it's only under these extreme conditions. And so it's only when we can start getting signals from the early universe, whether it's gravitational waves, whether it's the neutrino. I mean, there would have been, in the same way that we have this matter horizon at 300,000 years after the Big Bang, when the universe first becomes transparent, it became transparent to neutrinos when it was a second or so old. And so, if we could look at the neutrino background, we could get another shot at looking at the way the universe was. So, yes.
Yeah. I mean, it's interesting that technology has come along to allow one to do things. I mean, like just electronics, for detectors. I mean, I was actually working at the Super Collider before it closed in like 1990 as an engineer, and it's really interesting though that so much you do now is because you've got the electronics to do it. And if you look at that, the CERN, discovering the Higgs, if you look at the amount of data processing and electronic equipment to actually find that and compare it back to the original particle accelerators, like in a room with, I mean, I don't know, I mean, even if they had vacuum tube amplifiers to detect the things at the time, it's just quite an interesting thing how we've learned so much in a relatively short term, because we've had this stunning increase in electronics. It's allowed us to do so many measurements and data processing.
No, that's true. I agree. There is something, I mean, the same as I think some philosopher of science would find something to work on here, that we always, maybe our simulations of the universe and the lambda CDM simulations, whatever we're doing them at the limit of the available technology.
Yeah.
And I think what that is telling us is not how clever we are, but maybe how inadequate we are, because come the advances in technology, the simulations will be so much better. I mean, it's still impressive, but the simulations of the universe still fall far short of incorporating individual stars, for instance, in the simulation.
I've actually always had a quote that the amount of raw physics is enough to keep us engineers occupied for 1,000 years.
Yeah, well,
there's so much of physics now that people are just a stunning amount of applications of physics now that we're just scratching the surface and engineering them. I mean, a recent one is just random number generators for encryptation by using quantum tunneling, because you need to generate a random number. And so there's a whole load of things that are really interesting in that way. Yeah.
Now, has anybody got, I see, are there some questions in the chat, Jerry? Has anybody, you can look at that.
Let's start with this lovely one from Dick Grange, who asks, is it a coincidence that there are as many stars in a galaxy as there are galaxies in the universe?
Well, yes, I think it is. And I mean, you know, it's when I say 100,000 million in our galaxy, you know, you've got to say, well, what's the average size galaxy? And where it gets a bit hairy, and nobody asks me this, but when is a star not a star? How far down the main sequence are we looking when we're counting stars? Because, you know, we get to the point where stars and Jupiters start to overlap. So the numbers are kind of order of magnitude-y. So yeah, I don't know. It probably is a sort of coincidence, yes. And what's special about the observable universe? Nothing, frankly, because it's just the bit that light's had time to get to us. So we think, in fact, people would look at that microwave background and they'd say, it looks the same from one side to the other. So you might say the gradient of, say, density across it is less than 1%. So maybe the true universe is 100 times the size of the observable universe. But, you know, maybe it's 1,000 times. So, so what? So what's in a number? What's so special about the observable universe? So yeah, a coincidence, but a nice happy one, I think. Yeah.
Okay. Martin Venn asks, when you showed density of the universe, you said the units were solar masses per square parsec.
Whoa, did I? I should have said cubic parsec.
Cubic, yes, I would have thought.
Well, no, I may well have said square. Yes. Yes. Was that the question? Yeah.
The local number seems
not quite the question. It was the start of the question. Someone else has already pointed that out, but it just seemed like a big number to me. Even if it is a big, even if it was a cubic parsec, that seemed to be an awful lot of suns in our little local bit. Now, was this something else? Is this where you were trying? Was this the dark matter, or where did that?
No, it is the average density. I mean, we're talking about the average density of matter. Now, if you had a sun in every cubic parsec, that would be a hell of a lot of suns. Now, what I'm going to tell you is that, yes, I said 3 times 10 to the 10 for the density in the local solar system out to Pluto. But if the density of water on this scale is 1.5 times 10 to the 22. So
that's the bit I missed. Thank you.
There's almost nothing.
yeah, I missed that bit.
10 to the 10 is a hell of a vacuum.
Yeah.
So it's just, and the reason for using these crazy units is it goes from 3 times 10 to the 10 for the local solar system to 1.5 times 10 to the -7 So, you know, it was Brown, the Astronomer Royal for Scotland, who first pointed out to me the extraordinary contrast in density of matter when you average over the universe, or average over a space that includes many clusters of galaxies, and compare it with the solar system.
Okay. Thank you.
Yeah.
Okay. Well, at the moment, we don't have any other remaining questions in there. So I would say let's take the opportunity to really give our thanks to Robin for this quite an amazing tour this evening. So
Thank you.
Yeah, it was a good talk. Yeah.
Thank you.
Yeah, spot on. Fine, yeah.
So, Robin, you're welcome to stay on with us for other chat.
Well, I will hang around for a bit just in case, but then I do have to go in the not far distant future. Yeah. So just carry on. Oh, well, do what you do. Yes. Okay.
Over to you, Alan, then.
Okay, thank you very much indeed, Robin. A fantastic talk, that, and thank you. And thank you very much indeed to Jerry for organising it. I'd like to say thank you to obviously everybody who came along to tonight's meeting, and to give you a reminder that our next meeting is on March the 9th, where we've got Katie Clough telling us the solutions to Einstein's theory of general relativity. Details of that will be on the website, and hopefully this time we'll get all the links sorted out correctly.
That will be interesting, because I did a first course in Masters in General Relativity, and it used to take me the whole weekend, like 9 hours each day, to solve one problem that Hawking would do in his head in like 5 minutes.
Okay, well, I'm sure we've got one person at least who's going to be extremely interested in that. I will formally wind up the meeting now. And just remind you that the recording of it should be available on the website from Saturday. So formally, thank you very much indeed for all coming along, and good night.